it's bigger on my screen.
Sounds like a personal problem.
Yeah, exactly. So here, let's take a couple steps closer. A little better. Let's scale it up. We can have the geometry shader double how long everything is. No, it doesn't do the transform on this one. We have the tessellation evaluation shader double how far everything is. Right here. Okay, I function that sort of sounds like its name, so that it normalizes things. Now it normalizes it to a unit circle of 2 units instead of 1. That was the least number of characters I think I could have typed to double its size. Okay, well, we'll go ahead and get started, because it's time to get started. And so I want to talk a little bit about normalize real quick, since normalizing things can be funny sometimes. So I decided to change the cube into a sphere. So it's like a spherical cube. You know, assume a spherical cow if you're a physicist. For now, we'll have a spherical cube. We had this old demo for the lab, and I think I had it in normals. There it is. And so this is what it looked like. And the cube jumps between the like pointy cube thing and the non-pointy cube thing. Now, the points here outside the cube, it's bringing it out further than really necessary, and that's making it a pointed cube instead of just a rough approximation of a sphere. It's more like naval mine shaped. Everybody got concerned about naval mines like a few weeks ago because they found them floating in Puget Sound, and everybody thought it was left over from World War II, but actually it was a Navy training inert mine that had gotten lost a few years previous. Not nearly as cool. No explosives involved. Anyway. So we have this geometry shader in here, and I think I called it normal to GLSL. So this is kind of a longish shader. This is an answer to Lab 3, since it was the demo for Lab 3. And basically what it goes through down here for each of those points, we take this hypotenuse coordinate, or like hypotenuse center, I think that's what it stood for. And so we find the center of the hypotenuse. It depends on exactly which one happens to be the hypotenuse. There's a third case down there to take care of the last one. So anyway, I figure out which one's the center of the hypotenuse, and then draw the whole thing. I have this draw triangle function. It takes 3 coordinates and then 3 colors and draws the triangle. So we take an average of the 2 points on the end of the hypotenuse to get the center, and then subtract the normal vector, or twice the normal vector from it. And that's what pulls it out to be a bulge. So if we change that 2 there, for example, to say a 20, we would expect to see the bulge grow by a great deal. Similarly, if we wanted the bulge to go, say, to be like really small, if we said 0.20, then it should be barely bulged at all. It just looks like somebody's blown some air into it or something and very slightly bulged it. Okay, so if we wanted it to bulge out, though, exactly the correct amount to make it look like a sphere, one characteristic of a sphere is that the origin's at the center of the sphere, and in our cube, the origin is the center. On a sphere, if the origin's in the center, all the points of the surface are the same distance away from the center. So as long as you put a bunch of points at that distance away, you get some kind of approximation of the sphere. So one way to do that would be to just go ahead and normalize these values up here. We're taking MVP, or model view and projection matrices, multiplying them by each point here. So if we were to first normalize the point, you can see it's even colored special, so it means something to my text editor anyway. Okay, so with these all normalized, then we should be looking at all the points on the sphere, right? Make sense? So then the bulge shouldn't matter anymore. It should be bulged out to be the same size as the sphere. But if we try that, it actually doesn't work. In fact, it doesn't have any effect at all. Here's the reason. So when you normalize something, you take each of the values, you take a vector and you make its magnitude 0. So if you have a vector here, geez, math usually this thing's for vectors, so I guess we'll just do that. And it's like 0, 2, 0, and we want to normalize this vector. We have to make it go in the same direction, but make its magnitude 1. So there is a normalized version of that vector. It becomes somewhat more complicated if your original vector is not just something like that, and instead it's 0.1, 0.8, 0.4. Okay, how do you scale those to make the magnitude 1? You have to think about that one a few minutes. But even though it's hard in your head, it's not very hard for the video card to do. It's good at stuff like normalizing vectors. So you have this normalize function. But here's the problem. This isn't what we're normalizing. Each of these positions is a vec4, not a vec3. So what we're actually normalizing has this extra value at the end. So if we normalize that vec4, we get quite a different result than if we just normalize the first 3 components. So that's where the problem lays. And so in order to fix it, we expected this to put all the points on the cube. Didn't. Excuse me, on the sphere. Didn't. What we have to do is normalize a dot x, y, z, because that is, if we swizzle it, we'll get something else on. So that would give us the right thing as a vec3. But it's not even going to run like this. It gives us actually quite a lot of errors. I've never seen that many errors come out of a GLSL program, like ever. I'm sort of impressed. Anyway, yeah, because we got a vec3 times a mat4, a 4x4 matrix, and this is no good at all. So if we take this and we convert it to a vec4 and make that last piece 1 like it's supposed to be, and we do this for all of them, then we will have done our typing for the morning, and but we'll have this. Okay. So now you can see that when it does the bulging thing, they are all nicely placed around there on a sphere.
Except for the original corner.
Well, they're placed on the sphere too, because everything is going to get normalized the same distance out. My only wonder on here is why is it, oh, it's like a switch here that just draws the original. It turns it on and off. And in the original, there are no bulge points. So that's why it gets flat-sided occasionally. In order to test all this stuff, I did it on a different version of it that always has a bulge, but the bulge is set by the sign of something inside the program so that the points grow. And I think I had this one running in lab last week. And so on that one, it doesn't become flat-sided occasionally. It just stays all the points out the right distance. Okay, so let's look at our masterpiece here for a minute. Actually, I think I might just go ahead and do that. Okay. Oh, now it looks weird sometimes. Oh, well, whatever. Sometimes it looks weird. So we got our masterpiece here. It doesn't look a whole lot like a sphere yet, though. And the main thing that separates this from a sphere is the number of triangles. They're laid out kind of okay for a sphere here. We got a bunch of points. They're all exactly 1 unit away from the origin. And so we've got kind of an approximation of a sphere. It's just too crude of approximation. So one solution you might look at and say, well, what if we just make the geometry shader recursive and go do it again? We could use transform feedback and make that happen. And we could. I'm sure we'd get there eventually. But it would be really bad from a performance perspective. So we won't do that. We'll learn how to do it correctly today. So then once it's done correctly, it will look a lot more like this. Although this one's drawing a wireframe, and so that you can see where the actual partitions are. If we make it not draw a wireframe, it kind of looks okay, and we could turn the geometry way up and make it look way better. But let's talk about tessellation shaders first. Okay, one note about a tessellation shader. So, okay, well, let's go look up in the thing first. Okay, So the Chronos here is kind of the official reference for this stuff. I don't know if it's the official reference. It doesn't sound like it can be an official reference because it's a wiki. Anyway, the Chronos wiki has a lot of interesting information about these that's generally correct. Let's say it that way. Okay, so tessellation is part of the pipeline here. We look at our picture of the rendering pipeline. That's where we're at, right there, tessellation. And so we get our vertices go through the vertex shader, then the tessellation stage, which can involve two different shaders, and then the geometry shader that we've been playing with for a long time, and then all this other fixed stuff, and then eventually gets rasterized and goes to the fragment shader, which we've also been programming and having a great deal of fun with. Okay, so the tessellation process takes it can take a patch. And so patch can include a variable number of vertices. In fact, you can have as many as 64 or maybe even more. There's a constant defined that's the maximum patch size, and it may change. I think you're guaranteed to have at least 64, if I'm thinking about this right, but you might be able to have more still, depending on your GPU and OpenGL version and driver and all that kind of stuff. Anyway, so patch has a whole bunch of vertices. It can be small. My demo that I did with these things with the sphere actually only uses a patch size of 3. So patch is a triangle. But anyway, regardless, a patch is a section that's made up of vertices, just like a primitive, except that it can have more, and they're used as control points in order to form a mesh between them. So that's what a patch is. So this tessellation process expects as input a patch, and then the output that's going to come out is primitives, like triangles. And it's kind of expected that they'll increase in number. They don't have to. It's possible to actually cull an entire patch in a tessellation process. We'll go over that. Okay. So, up to 32. Okay. It depends on the implementation there. I thought it was 64. Apparently I was wrong. I think 64 is the guaranteed minimum maximum tessellation level. We'll talk about that one later. Anyway, so if you write out 64 crossed out, right 32. Okay, so the tessellation control shader takes in a patch, and then its output is some values relating to how everything is supposed to be tessellated, not actual positions. Then well, you can output positions too. And then the tessellation primitive generator, which is not programmable, is the actual tessellation process. Then, with all the polygons that are generated, usually there'll be a lot of triangles coming out of it, a lot more than went in terms of the patches. You'll run the tessellation evaluation shader on each vertex of each of the triangles that comes out. So you should expect the tessellation evaluation shader to run many more times than the tessellation control shader. And then the geometry shader comes after that, and it can, again, amplify things if it wants to, or call things, or whatever. Okay, so that's the order here: tessellation control shader, primitive generator, tessellation evaluation shader. So the tessellation control shader allows for the tessellation level, and this is an indication for how detailed the tessellation ought to be, how many polygons we ought to subdivide everything into. And then the actual vertices, so you can move stuff. You can also just pass them straight through. The vertex shaders already has a way with them, and so you can move them there. It's got a funny invocation thing too. It actually is invoked once per vertex on each patch, and so you're expected to use the invocation ID as the index instead of a loop with all this stuff to avoid some of the problems with geometry shader performance. And then optionally, you can use GL patch parameter FD to set default values. If you do that, use GL patch parameter FD, you don't actually need a tessellation control shader. If you want to skip the whole process, you can say, okay, we're just going to tessellate everything to level 10. And that's that. And then you don't need tessellation control shader to say, for each part of this patch, how much does it need tessellated exactly, you see. And it forgoes a lot of detailed control, but it avoids an extra stage. Okay, and if you needed to do transformation, of course, you just do it in vertex shader. Okay, so that's what the tessellation control shader does. And then the primitive generation. Okay, so here's a funny thing about the primitive generation. It's actually done without any regard to the coordinates that your vertices are actually at. And so the output looks look a lot like this. So suppose you got some triangle here, and it's getting tessellated, and so you've got a vertex that's actually right here, by however the tessellation process works. Maybe it defines a triangle that goes like that or something like that, you see? And there'll be a whole bunch of them in there. But anyway, talking about that vertex there. So the coordinates for this vertex here, as a vector, that vertex, the red one, you'll get the influence of each of these. So suppose these are numbered 0, 1, 2. I remember that from doing the geometry shader stuff. They each got their numbers. So if those are 0, 1, and 2, then that's what the 3 spots in this vector are taken from, 0, 1, and 2. And so it's pretty far from 0 here, so maybe 0.2. It's pretty close to 1, maybe 0.8. And it's kind of further again from 2, maybe it's 0.3. So it's actually given as the amount of influence that each of these vertices should have over where this point goes. So then when your tessellation evaluation shader, which is not optional, you can take those values and come up with some position that you want to put that vertex based on the actual patch coordinates. So it's more defining a mix of these 3 values and how you got to use them, as opposed to giving you exact coordinates. Okay, so that's what they do. In quads, the barycentric coordinates come out a little bit differently. It's basically the distance over in each direction that it is. And so you actually only have 2 coordinates for each of the points inside it for a quad. You can run it with either triangles or quads or isolines, which work differently. Okay, so the tessellation levels. In general, this is the number of segments that an edge gets tessellated into. So if you were to send this triangle in here with tessellation level 5, you'd expect that this edge here gets broken up into 5 segments. And so there's a similar pattern for the rest of this stuff that works with that tessellation level. So you have different tessellation levels that you can do inside, though. You can actually tessellate the inside more than the outsides, or one side of a triangle more than the other sides, or that kind of thing. So that you can match your geometry as you go. I think the best thing here would be to show you pictures. And there's some good pictures on here. Okay, so there's things being subdivided, of course. But here is a triangle tessellated with level 3. And so you can see what we've got here. Each of these sides are broken up into 3. And we've got a little subtriangle in the center. And all of these things, you can see this is actually a quad right now here. In fact, these are all quads except for that. These will have to be divided into 2 triangles each in some way. And so you got a tessellation level there. Here's tessellation level 4, just set up on the whole triangle. So each of the edges is broken into 4. And then you've got the subtriangle, and it has a point inside it. A subtriangle is just a point. And then it forms quite a lot of quads. I think every single thing in this one's a quad now. And so they'll all have to be turned into triangles. But for turning a quad into 2 triangles is pretty easy. You just draw a line through one way or the other across the center, and then you got a triangle. So that's a couple of ways to do it. Now, if the edge is different, then things show up different. So here's an example, tessellating a triangle. So I go all the way down here, show you how it comes out. Because this picture down here is just that one, except for the dotted lines that are probably hard to see anyway. Okay, we'll go do that. That'll be a little bit easier to see. Okay, so what we've got here is a triangle that's tessellated differently depending on which edge. So you can see this edge here has been tessellated at level 4. This one over here has been tessellated at level 6, and this one's all the way back at level 1. So in order to do that, what we do, so the inner tessellation level is set at 5. So the inside of this is tessellated just like the whole thing was going to be at level 5. Then the edges have the number of vertices changed to reflect what we actually want in terms of tessellation levels here. And then we go ahead and make triangles appropriately. Now this one comes out pretty funky down here because you got tessellation level 1. So this one edge is divided into one segment. It doesn't really get tessellated. And its inside is at a pretty high level here. So you can see we got this funny triangle there. It's not really made symmetric. You have some really strange shaped triangles for some of these that are very thin. Things like that can happen when you're tessellating. The tessellating uses a fixed algorithm in the tessellation in primitive generation here that does all this. You don't write this part. And so you're sort of stuck with how it works. Now, wanting a triangle like that is sort of a strange thing to want. So, you know, if you want something strange, you'll probably get something strange. I feel like this is like one level stranger than you might expect based on your saying that you wanted it. Yeah, that's how things are. So the reason that you might want to do this is if you got some patch and it's heavily tessellated because it's close, but it sort of wraps around to something further away, and that's not going to be tessellated as detailed, then you can match up the edges. Because if you don't match up the edges, it might make some kind of funny artifact. Okay, that's tessellation for triangles. You can go through the vertex here. I want to get to showing you how to actually operate this stuff and not talk about this quite all day. So quads are kind of similar as you might expect. They come down to sort of a grid, but of course, when you get the whole thing done, since the edges don't actually have to match how the center was tessellated, you can have something funny like this. And so with these ones here where the tessellation levels are not that far apart, it really looks quite normal and did a pretty good job. If you give it sort of an extreme case here where it's a really low tessellation level and a much higher tessellation level up here, then again, you end up with a little bit strange artifacts, which is what I think they're trying to show you with this, that if you make a really strong divergence in tessellation level, you might get something a little bit funny. Okay. So you can see that at the end here, they are fully turned into triangles with these dashed lines, even though it started out with a quad. Everything inside here has been turned into a triangle. And so then you're ready for a lot of triangles. So if this thing went through the tessellation stage, this quad, and so the patch was just 4 vertices, then the tessellation control shader would operate if you'd be given 4 invocations, 1 at each of the vertices in the corner of this patch. Then the tessellation evaluation shader would operate on every one of these generated vertices, and so you see it would operate on quite a high number of vertices. And so that's where we get to the tessellation evaluation shader. It might run a whole lot more times than the tessellation control shader. Okay, let's skip ISO lines because I want to get to actually showing you how this thing works. Oh yeah, discarding things. Discarded. This is like worse than regular discarded. This is where you like discard it and you go fire the author. Anyway, so the discard here. So tessellation level 0 gets rid of the patch. So if you're in a tessellation control shader and there's some condition under which you're like, yeah, we got to get rid of this thing, you can't get rid of it in a vertex shader because the vertex shader can't cull things. But the tessellation control shader can. The tessellation evaluation shader can't. In a tessellation evaluation shader, you're stuck making 1 GL position for every input you get. Then in a geometry shader, you can cull things again. But then in a fragment shader, well, I guess you can cull it by just painting it the background color. Anyway, but if you really cull it, no, that's not how you cull it. You draw it transparent, like perfectly transparent in the fragment shader. That will cull it.
You cull it in the geometry shader, but just not moving vertices.
Yeah, yeah. So it sort of changes what the rules are from one of these things to the next. Okay, so that's that. That's how these things come together. So the tessellation evaluation shader has an output of GL position and then anything else that we've got. And we have to calculate it from the GL test chord, which is the tessellation coordinates in barycentric form, like we were showing over there with the triangle. And the GL in with the patch vertices, the originals for the patch. Okay, so let's tessellate this thing. Okay, so we have this one. How are we doing? Maybe I would show you this one. I'm concerned about getting lost too long and losing our momentum for a really long time if I go and write it from scratch, as opposed to just showing you the one I already have that works. I got it working because I was figuring that this would be an oven type demo where, it's a cooking show. They show you how to make something and then put it in the oven for an hour, but then they pull out the one that was in the oven the whole time. Okay. Let's see. Okay, so where to start? Let's start with the control shader. Okay, this is the tessellation control shader. Actually, let me show you what the vertex shader does here first so that we're not messing things up. Okay. So the vertex shader, this is the same vertex shader we've been using for a long time. It takes in the chord 3D, which is the 3D coordinates, so not a vec 4. I'll have to make it one later. And this keeps making me think that somehow this computer must not work because there's this cord sticking out of the cabinet with the computer and it is not plugged in. But since everything works, it must not be important.
Yeah.
Anyway, so we got the chord 3D and V color. Now the color thing is irritating because you can't call it the same thing all the way through. And so we keep having to change the name of what we're using for the color at each step. Anyway, so we got that. We got our MVP that's not actually used in the shader, it used to be. And then we got the color coming out as FCA. And so there's how we do GL position. It's just the same thing. Okay, so vertex shader basically doesn't even contain anything interesting. So then the next thing in the pipe is the tessellation control shader. So the tessellation control shader, first of all, we'll talk about our layout. And so the layout on here is 3 vertex patches, triangles, basically. And that's what the cube started with, so we're going to stick with those. So that's the layout. And so we get to use GL in and GL out without declaring them anywhere up here as the input and output for this thing. Then we've got the FCA, which is our color, and then I needed a different name for the color to keep on passing it through, so I called it FCT, which will be the color that comes out for each of these things. So then we got a tessellation level, and we can set it actually 4 times here for the triangle. So when you set a tessellation level for a triangle, you set the outer 3 edges, and you can have them not match. You saw that in the pictures. And then you set the inner. The reason the inner is an array is if you're doing a quad, you actually can have 2 inner levels, 1 for each direction. But since we're not doing a quad, we're only actually using item 0 in this array. So we got a tessellation level there set to 4 in every single case. And then this next part. So this GL out and invocation ID and GL position. So we have a we have an array here that shows us what's coming out, this GL out. And that's all the GL positions for the patch coordinates. So this will be run once per vertex in our patch. Since there's 3 vertices in the patch, we actually have 3 invocations to deal with here. The invocations are numbered 0, 1, 2, so they make good array indices. Actually, here's something funny. If you decide to try to change one of them to a static number, it tells you they have to be like GL invocation ID. I didn't actually mean both. Let's get rid of that one. Okay. Take this one and say position 0. Okay. Really ought to be legal, you think, right? Take that one out. Okay. It says error. Tessellation control output right to FCT must be indexed by GL invocation ID. Anyway. So it's actually pretty serious about that. Okay. In terms of the other side, though, let's just change that one. 1 should exist. There should be 3 of them because our patch is 3 vertices. Hey, now it's
got a hole in it.
well, I mean, it's pretty messed up. But you notice that there wasn't any issue from that. Like it was okay with that. Okay. What if we said FCT? Could not bind attribute V color because we didn't use FCA when it came in. What if we say FCA right there? Okay. Notice it actually accepted that and ran it. It's still messed up. But FCA or FCT down there on the second line, that was actually our output. And so we just read from it. But the fact is it wasn't our output in 2 out of 3 cases, because if our invocation ID was 0, then we just tried to read the output from invocation 1. Was invocation 1 done yet? We don't know. So, you don't want to do that there. But I put this note up here. It's possible to use synchronization. You actually can use synchronization here so that you go and write something into your position, and then you synchronize, let everybody finish, and then read something out. So it's possible to actually have synchronization between each of the instances that's operating on a particular patch. Now, you should really think hard before doing that, because it can lead to performance issues pretty quickly if you have all of these indices, all these instances go somewhere and then wait until they're all there and then go do something again later. But it is possible on this, since you might want to do something kind of complicated here. Okay, we got this tessellation level 4. Let's go ahead and set that down to 1 real quick. So there's tessellation level 1, which is not tessellated at all. And so that's our original box. The box is made out of triangles, 2 per face, and so we have the diagonal there. So let's go ahead and set it 2. Okay, so you can see even at 2, it's kind of starting to look like a sphere in a way. See, it's not entirely bad. If we go ahead and set this to 64, then we see a sphere like this. Yeah, it's really not too bad, actually.
Oh, very lines.
Yeah, it's made up of lines. Lots and lots of lines.
If you took out the lines and just drew those, would be great.
I have the geometry shader doing that trick. Okay. Yeah, you'll see the color pattern on it. I put the lines in there so you can see what it was doing, but here it is without lines.
Ooh, bad monkey.
Well, we could stop that too. That's not too hard. Okay. Anyway, I'll put it back to lines. That's all the geometry shader here actually does is turn this into lines. Okay. So that's the control shader. That's what it's got to do. So for this, basically we're copying GL in into GL out. And so if we wanted to do some kind of transformation here, or if we wanted to apply our model view and projection matrix right here, we could actually do it right here if we wanted to. That would be fine. And so we have the opportunity to transform things as we like. But these lines here copied straight across. So this is about as simple as you can get for a tessellation shader. Okay, so then the evaluation one, TES. And this is also short, but it's not quite as simple. It does some normalize. Okay, so normalize instead. Okay, so on this one, with the in up there, our layout is triangles. That's what we're dealing with, these 3 vertex kind of things. Equal spacing. It's possible to space the, to do the tessellation levels actually in a couple of different ways. But we're doing equal spacing from one to the next. And then we get to specify our triangle winding order. We really don't care. Our triangles don't have a front and back. We're rendering the front and back exactly the same. Actually, we're getting rid of our triangles, making lines for the most part on this. But even if we do render the triangles, we're rendering the fronts and the backs the same. If we cared what the front and the back were, like if they were different colors or something, or the lighting hit them differently, then we might care very much which order the vertices were specified in. And so remember with the geometry shader, I was mentioning we might have a backwards triangle when we do the triangle strip in the kind of Z pattern and draw the 2 triangles. The tessellation process, it can take care of that for us and wind all our triangles the right way. We said that. Okay, we get our MVP matrix because we'll actually do the transformation right here. And then we have this color thing continuing to get passed through. So we got our FCT color that comes in, and then we output F color, which is going to get picked up on by the geometry shader, which is going to get changed by name again, and then it gets passed on to the fragment shader ultimately. Okay, so that's our inputs there. So then this whole position thing, we want to place all these things on the sphere. So that's why they get normalized, kind of normalized. So in for test, I wrote that function a couple hours ago, thinking that it might be handy. Basically, it takes a vec4 and it looks at it like a vec3, like takes the first 3 components, x, y, z, and normalizes those, avoiding the whole problem I put on the board up here. And so then once those are normalized, we go ahead and add the 1 back on the end. And then because the sphere was too small when I got to class and put it on the projector, we multiply the whole thing by 2, which makes it twice as big. Okay, so that's the process up there. So this P thing, we get this vec4 P, and what we've got here is a sum of the influence of each of the points. So we take GL test coordinate x, y, and z. That's the barycentric coordinates, like over there on the board. So they're not really an x, y, and z coordinate. And we actually could have called them R, G, and B if we wanted to. It would have been just about as relevant. GLSL is happy to have the first three components of the vector specified as R, G, and B. Anyway, so we just call them X, Y, and Z. And so that's how much influence each of the vectors have. So what we're doing is basically a weighted average here. Each point has its position weighted by which vertices it is closest to. And so when we take the sum there, and instead of dividing by 3, we just go ahead and submit it for normalization. Because it's going to get normalized anyway. We don't really need to divide it by 3. It wouldn't make a difference seeing it's getting normalized. If it wasn't getting normalized, we very much want to divide it by 3 and get an actual average here. Weighted average. Okay, so that's what this part does. And so the normalization here guarantees all the points around the sphere. And so we'll just have a whole lot more of them. So then the color. The color happens almost exactly the same way. The color is a average of the 3 colors involved. And again, it's just weighted by the tessellation coordinates. Okay, so that's the evaluation part. So then once they're evaluated, there's a geometry shader. And the only reason the geometry shader is here is to turn everything into lines. You can actually change the GL polygon mode. It wasn't the first axe I dragged out of the shed because I thought it was part of OpenGL 1 point whatever and it had been deprecated. As far as I can tell, it's actually not deprecated. So we can replace this with 1 line of C code in the program and just change it to drawing lines. No. But the geometry shader here just draws a line strip. The reason it draws 4 here is to draw a triangle here. You know, we have the starting point, that's vertex 1, and we got a side of it, that's second vertex, third vertex, and then I wanted to draw this last thing closed. So that was the 4th. So that's why the last one is specified redundantly.
Don't you not have to do that? Oh, I see.
It's not a line loop, it's a line strip.
You don't have to do it for a triangle, but you're drawing the lines.
Right, exactly. Yeah. So that's why when I changed it to triangles to show you, I commented out those 3 because they were, and they didn't cause any harm. 1 extra vertex doesn't specify a complete triangle, so it's not going to change anything. It just gives the card more work to do. They can do lots of work. It's good at that. Okay, so once that thing comes out of there, cube F, there's the old fragment shader with the color change. Basically, Lab 4 style fragment shader, changes color profiles. And
so basically, these tessellation shaders just do that weird extra triangle that we did the other day much better.
Much better. Yes. Yes. Much more triangles. So we can have something like that. A fine mesh. Many triangles. Okay. So that's what the tessellation control shaders do. Oh yeah, the other part. Okay. CPP. Okay, so inside the program part, there is a little bit of inside the program work to set these things up. So our pipeline here is getting fairly complete at this point. I ordered these things so that they're actually in order of which order they happen in. So we got our vertex shader, then we got our tessellation control shader, then our tessellation evaluation shader, then our geometry shader, and then finally our fragment shader. And they'll have to be compiled, and of course, if it doesn't compile, it causes a problem. So then we go ahead and make our program here, and we GL attach shader each of our 5 shaders. So then after all the 5 shaders are attached, we can go ahead and link the program and use it. So really just a bit of duplication in there and pulling in these other things. But the other thing that happens, so you know, we have to set the patch size. Let's not set the patch size. Okay, let's not do it. Can't make me. Oh, it worked. Oh, I didn't make. I did make. Well, I feel crazy. I thought we had to set the patch size. But it seems to have figured out the patch size, even if we don't set the patch size. Anyway, so according to the documentation at least, you ought to set the patch size. I actually put that there where the demo was broken, and then later I found that I made a silly mistake somewhere else in one of the shaders. And so then I fixed that and everything appeared. I didn't go back and check and see if they could take that out. Guess you can. Okay, so I set the number of vertices per patch, and then when you draw, instead of saying GL triangles or something like that, you say GL patches, because that's what we're going to be drawing now is patches. And so those all appear. Okay, and so then so after that, I guess we pretty much get to our thing, which works pretty well. Okay, this isn't, by the way, this isn't necessarily the best way to draw a sphere, starting with a cube like this. You can see a lot of artifacts where the triangles kind of change direction and give you little, you know,
Cube.
yeah, just like visible areas that are notable as having,
You mean like the diamond looking?
yeah, feel like some kind of weird soccer ball.
Oh, yeah, I see.
So what should we start with?
So most of the actual spheres, like one thing you can do to improve it, instead of starting with a cube, you can rotate the top of the cube. And so think of it like a twisted rectangular prism, twisted 90 degrees. And that avoids some of the cubish nature. You can also start with a certain number of circles or that kind of thing. You can probably start with a point and just have an algorithm that makes the whole thing from it. Could be done. Yeah.
It's weird because I think it looks like a very round square.
Yeah. Yeah, I know. It looks like something a soccer player would make after a victorious game.
It's just sick.
The thing about soccer, we don't have soccer here a lot. The other places in the world they call it football. It's actually a pretty rough sport. The goal is to kick the ball as far as you can and hit your opponent in the head. And then once they die, you actually take their skin and you sew it into a soccer ball. You can see they're made into distinctive patches. Typically, the color the kids wants just like black and white, figuring that we had teams of different skin colors, but the actual ones are like more variable.
Seth, your programming analogies are getting too every fifth driver.
Remember back in 250 when it was just chicken metaphors? Come so far.
You guys remember in networking?
Well, I have to expand this so that you understand the sport that the rest of the world plays.
That's what plays.
Okay. So that's I guess that's kind of the quick overview there. Okay. So using these things, and why would you want to, and why are they better than a geometry shader? So the tessellation, the problem with the geometry shader is number of invocations. Since what we were doing with it, we took the geometry shader, because it's invoked once for the primitive, and then we do a kind of a complicated bunch of math inside it. And so what we have is, seems like a lot of processes, but it's really not very many for the GPU. So we've got not enough processes, and they take too long to run. And so that slows everything up. If you give 100 of your shaders something lengthy to do, then you got to have the rest of the 1,800 or however many more you got sitting around waiting. And then once it's finished, they can finally do something. So adding a geometry shader causes performance difficulty there. Another way a geometry shader adds performance difficulty is it requires the card to be ready in a memory sense to absorb a different number of vertices than went in. So if you think about the pickle that the device driver has to solve for, say, a vertex shader, you got an array of vertices, and you're about to get a new array of points. So you need a memory buffer that's the same size as the original was. Pretty easy, right? For the geometry shader, though, we have to be ready, in the card sense, to receive some possibly unknown number of vertices. That's why we're required to set max vertices in the geometry shader. But there could be a lot less than max vertices, Yeah, if max vertices is 10, and they actually only emit like 2 each on average, then perhaps the driver allocated a bunch of video memory it didn't need to, or perhaps it didn't have enough and was really hoping that was going to happen. Anyway, there's a lot more management that has to come from absorbing an unknown size. With the tessellation, once the tessellation control shader has said what tessellation level everything is to receive, then it's actually possible to calculate how much space is going to be required. And so it's actually known before the tessellation process happens, the primitive generation, how many invocations of the tessellation evaluation shader we're about to need. So knowing all these things in advance allows the driver manufacturer to implement all these things in an efficient way. We also get a tremendous number of invocations. Notice that it's sort of set up like with the tessellation control shader. We don't get to set invocation ID, and we don't get to say that we only want one invocation per patch. We're required to have one invocation per vertex. We're required not to index our outputs by using regular numbers, so we can't just say, okay, for all invocations except for one of them, we're just going to go ahead and terminate. And then the last one's going to run a lengthy process to figure out where all the vertices go. You know, the driver it'll try to fight you on it. Maybe it'll figure out a way to make it happen using synchronization primitives.
Well, you can probably multiply the negotiation ID by 0 plus a constant.
Yeah, you can probably figure out some way to trick it into doing it. But in general, that's not really the way. It's kind of strongly discouraged. So assuming that you use it kind of the way the Chronos group intended, you'll end up with as many invocations as you can have. And then this actually does something pretty simple too. It's not actually doing geometry amplification. It's just specifying tessellation levels and where everything ought to go. So there's not really a whole lot of complicated logic you'd have in this thing. So then the primitive generator does the more complicated logic, but since it's a fixed pipeline, there's a pretty known target here for optimization for the GPU manufacturer. So they implement that however makes sense on their hardware, and they have a tremendous advantage implementing this stuff. You know, NVIDIA knows how their card works. We don't know how NVIDIA's card works. NVIDIA won't tell us. And even if they did, it'd probably be pretty complicated. And you know, we're not supposed to worry about how the card works either, because we don't know what NVIDIA is planning on the the GeForce. We don't know what the next one's even number is. It's going to be the 21s or the 3 series.
21s.
21s?
Yeah, and it's RTX.
Oh, really? Did they announce that?
Yeah.
Okay, cool.
The ray tracing cards?
Well, those are the 20 series.
No, those are the 21 series.
So the 20 series.
Or can you turn it off?
The 20 they just came out.
Yeah.
So they skipped the 19 series?
Yeah, there's no 19s.
Okay, that's what it was.
Or 18s or 17s or 16s or, yeah, or 11s.
I got you.
I thought I heard they were gonna do like the 20 series and then like the 11 series would kind of be like a continuation for like a GTX, but the RTX would be like a somewhat of a more higher end.
Oh, really?
That's what I thought. I heard, but I haven't really seen anything else about that.
Right.
It might have just been a rumor at one point, but
Yeah.
they might just be going all in on RTX.
They've moved all the price levels up one. The actual reviews are out now, so if you're interested in how a 2080 does on real games that people actually have benchmarked by somebody other than NVIDIA, you can find it now. But yeah, like the 2080 is like the price of the 1080 Ti was.
Yeah.
The reviews are out except for the fact that there's no games that have ray tracing properly built in yet.
Yeah,
So
yeah.
no one can benchmark it with ray tracing.
Some have some, you know, I don't know if they have full implementation, but they do at least support some of the hardware,
Okay.
like Shadow of the Tomb Raider.
That update is coming out in a DLC or like an update later.
Oh, and
wasn't
that
released
they-
at release.
I thought
Well, that makes sense because I looked at an article and it had Shadow of the Tomb Raider, and I was thinking, oh, good, we're going to get RTX benchmarks and ray tracing, but it didn't have it in the article.
Isn't NVIDIA supposed to put out like a pre-release card for game devs?
I don't know if they've done anything with that or not.
I think NVIDIA is making games not release things yet. Because
Okay.
one Tech Tips like has a 2080 and they went and benchmarked and stuff. And they were going to benchmark ray tracing, but couldn't because no games had it. So they directly contacted a game dev studio that was making a game with ray tracing. They agreed to like come in and show them an exclusive demo with ray tracing, and then canceled on them for mysterious reasons.
Oh, okay. They're keeping a lid on it. Yeah, but I guess the point here is NVIDIA has some future in mind for this, and ATI has a future in mind that involves catching up. And so neither of them know exactly what the card architecture is going to morph into. Yeah.
This whole ray tracing thing is kind of getting on my nerves because I just bought a 260, like,
A 260?
sorry, a 1060.
Oh,
Okay. I just bought a 1060 and they're like, oh yeah, this will last you a couple of years. Now suddenly ray tracing is just like,
it still might be fine. Even when it comes out, it might turn out that you can either have 4K or you can have like 800 by 600 with ray tracing, you know? And I think that's what everybody's wondering.
My 1060 can do it in 4K.
Yeah.
It's just it can't do ray tracing. So
Right.
what's the point?
What's the point?
If you have the lower resolution enough for ray tracing,
I thought it could virtualize ray tracing. It'd just be a lot slower at it because it doesn't have any of those trends.
Maybe it depends. It depends. 'Cause I have a different card than just regular 1060. I got the 1060 doing it. Well, that's optimized for certain different things.
Well, remember, in a pinch, you can just run ray tracing in the
Oh, yeah.
CPU, so.
yeah, that's true.
I have an 8-core, so that'd be probably possible for me.
Well, that would actually be good because the thing that Overwatch players never do is they don't take a page out of the chess players' books and play multiple games blindfolded at the same time.
No, that would be fun.
No, you see,
So if you had the ray tracing and ran on the CPU, you just play your whole game blindfolded and you can see what you did the next day.
you know, but that would be a good idea, which Overwatch players just don't. Because you can't see anything in the screen.
So it kind of reminds me, I was at that one computing museum and they had some sort of old computer that had like multiple processors. I'm trying to remember what the technology was called. And it was actually running a ray tracing demo on it.
So I wanted to pull up a benchmark thing here so that everybody who hasn't been looking at hardware benchmarks for stuff that we probably can't afford anyway can see how well these things are doing in a frame rate sense. I wanted a simpler bar that I don't have to explain for a moment. So I might go and grab one from somewhere else, maybe I've already seen. The performance of the new cards is better, as you can see. The 2080 is defeating the 1080 Ti in this particular benchmark, and it seemed to do that fairly consistently. Just a little tiny bit better, but not a lot better. On current games without ray tracing, of course. And 2080 Ti is sort of in a class by itself, which maybe they figure justifies the price point all by itself. And so, you know, other things fall behind that. Our 1070s in here, as you can see, are kind of behind the curve on some of this other stuff.
So what was the first one doing better than the 1080 Ti?
Which one? This one?
Yeah, which one did?
This is frames per second here.
No, I mean, the card number.
It's a 2080 Ti.
Yeah.
Okay.
Yeah.
So the 2080 Ti has to beat out the 1080 Ti.
Right. They handily improved their model number equivalents. Like, you know, 1080 versus 2080, you can see it's a big difference. 1080 versus 2080 here is a big difference. The 2080 is defeating everything current. So you don't even have to go to the top level to get a faster card than we previously had.
And which one was the same price as the 1080?
So the 1080 Ti is around the same price as the 2080.
Okay, so if you're looking to upgrade a graphics card, you might as well just get a 2080.
Instead of a 1080 Ti. Yeah, I suppose so, since they're close to the same price. 2080 has the ray tracing engine in case you ever need it, and they're close to the same performance on current games. That makes sense. How much is it? They're like $600.
They're not cheap.
Oh no, definitely
I
not.
mean, that's cheaper than the 1060s were a few months ago.
Yeah, that's true. You know, I wonder if this whole ray tracing thing is a scheme against crypto miners, because I don't think you can mine cryptocurrency with ray tracing engines.
They were all buying out the AMD hardware anyway. The price performance thing is better for AMD, but they mostly moved on to dedicated hardware.
Yeah.
Actually, on Craigslist, there's somebody selling a whole bunch of cards from mining.
Ooh.
The prices weren't that great, actually.
How hot did the card? The question is how hot were the cards running the days that they were?
Well, this one,
It's like, if they were running all the cards on that,
If they were
using
burning
all the
cards.
cores, yeah, using all the cores all the time, then it's not worth it. But if they were running like half the cores and really well cooled PC.
Hey, it's up here.
Nah.
I'm in housing somehow.
Although, when we get a house, I'm trying to think we find the way to the heater.
That that's actual.
There it is, parting out
Just
big
turn it
mining.
on right away.
So, yeah, they get hot, you're right. So see the framework here has them all connected with these extender thingies to actual slots on the board. And so this is a cloud-based architecture. You see they're up here forming a processing cloud above the main system. Yeah, and like I said, the prices this guy's asking are actually not that awesome. You know, it could be somebody in his room. I never even thought of that.
Hey, that's Marcy.
No.
Okay, so tessellation and how this all relates to it. Yeah, the cards change a lot year to year. And so if, unlike the geometry shader, we have the video card company handle the expansion from a patch into a geometry, as opposed to writing our own thing in geometry shader, they can make it a lot more ideal for the architecture. And then they can try to optimize it in subsequent releases and whatnot, and keep improving performance for us. So that's kind of the major advantages here with the tessellation shaders versus the geometry shader. It easily gives you a whole bunch of invocations, and it turns over the complicated geometry amplification part to the video driver. Lets them do as they will with it. So typically, if you have the choice between tessellation and geometry shaders, you should use the geometry shaders. They are an update. Ideal version. Okay, this is actually really interesting reading, this particular article. But the geometry shaders, I think, were about OpenGL 3.2, and that's a little big to be seeing anything. Okay, a lot of things get deprecated as they go. Maybe it's back here. Anyway, some of the features we've been adding, you can see come up on each of these things. Addition, geometry shaders, OpenGL 3.2 in 2009. And so the geometry shaders initially came out to do this whole amplification thing, but since they had performance difficulties, keep going up here, tessellation with shader stages, OpenGL 4.0 in 2010. And so there actually wasn't a very long heyday of the geometry shader. It was only a year later before there was a improved version of the thing. So that's the kind of thing you expect there. Okay, so I don't remember GeForce equivalents or whatnot, but they're quite a ways back at that point. Okay, and then there was the feedback leading up to our next type of shader, which is from 2012, which is the compute shader. And then since then, I haven't talked about hardly anything since, but if you feel like looking through and seeing what was added to it, you can just look through this list here. 4.6, so we don't have here, has, for example, SPIRV available. SPIRV is an intermediate language, and so it's a compiler target. Basically, you compile to this intermediate language, and the driver compiles it the rest of the way. And so it's a lot like GLSL. It's just that you can have this kind of half-compiled shader sitting around half-done. And so that might be what you want to ship to your game, is a half-done intermediate language representation instead of the actual shader. I think you were saying that they needed that.
Yeah, I figured they need to have like an x86, but for GPUs.
Yeah.
So standardized, you just compile that.
I think that's about as close as they figure they can get. Okay, vertex shaders can get the draw ID and base vertex index value from rendering commands, you know, there's all this other stuff. The anastrophic filtering here doesn't mean it's new in OpenGL. We've been using anastrophic filtering for a couple of decades, but it's some kind of improvement relating to how these things are set up inside it. I think I have it on this computer right now, actually. Okay.
What's it do?
It blends samples together, anastrophic filtering. So maybe it's just been in the ext texture filter anastropic extension the whole time. The other thing that the games can do is just tell the driver to turn it on and not actually define how it works themselves. And so you just have a checkbox in your game, and all the checkbox in your game does, I feel like I showed this thing already, is give an application setting here, which can be overrode in the driver control panel or not. But that way the gamer can just do it from in the game. Or in the game, I suppose you can turn it off for them if it's taking too long. your frame rate is too low. We're going to stop your game and adjust the driver settings and then start it again. I'm getting the feeling that wouldn't be very appreciated. Okay, so I think that's that's most of what I wanted to show you in there. Okay, so I put a couple of practice problems on here, adding a uniform to control tessellation level. This wouldn't be very hard. The tessellation level comes in just into the TCS, and so all you would have to do is just make a new uniform, whatever, right there, and that would take care of that. Or you could use a geometry shader to place a sphere inside a much larger sphere. Now that sort of ignores the fact that the geometry shader probably ought to just go away from this. If we clear this and let's go ahead and pull the geometry shader completely. So I'll take it out of the pipeline right here. We won't create it, and then we won't catch it. So it shouldn't happen. Okay, everything is, because I didn't fill it. It should cause a problem. Okay, the geometry shader recolored everything since we were recoloring things at about every step. If we look at cube.g, we made the final one FC final instead of F color. So if we look at the fragment shader, we just have to call this F color. Okay. So there it works. You can see we're set up in triangles instead of the the wire mesh.
It's also spinning really fast.
Why are you
And
spinning so fast?
I'm not sure.
That's gotta go fast.
Well, I thought I changed it to spin kind of slowly in here.
At the fair today, we did not notice at all.
Okay. So that's gone. Now to get the wireframe back, I should put the command right here. So I was going to show you later.
Just like
So if we just change the geopolygon mode and draw them front and back like before, but using lines, then there we have lines. I changed the drawing speed on there too a bit.
I love how it starts out barely moving and now it's just, it starts to accelerate.
Yeah, it'll eventually stop and turn around. There, it's coming.
Yeah.
I slowed it down. I to a tenth the speed actually while I was in the program. So there we go. Okay, there's another way that's pretty popular to make the lines, and it's in a number of demos and whatnot online. So it's a harder way. Inside the shader, you can actually bring the barycentric coordinates from the tessellation shader to here, if you want to. Just set them up as an output from the tessellation evaluation shader. And then once they're in here, you can do a little bit of looking to see if your fragment was on a line between 2 points of the triangle, or if it was somewhere in the center. If it's on a line, you'll have two of the barycentric coordinates be like 1, or about something higher, and you'll have one of them be like 0. So if one of the barycentric coordinates is close to 0, then that means that your fragment is close to a line. And so then you only draw it if one of the barycentric coordinates was close to 0. So it's actually a pretty simple thing here. The main thing I don't like about it is it means passing the barycentric coordinates on one more stage than they have to go, and so it means defining an output for an tessellation evaluation shader. Remember, in terms of memory use, the later you go in this pipeline, the more expensive each of the coordinates are in a GPU memory sense. Let's go ahead and split this real quick and pull up the cards management stuff here. And it's got a description here of how much memory is used somewhere in this panel, right here. And so right now we're only using 135 megabytes of card memory. If we start running this thing, we went to 285 instead of, maybe nobody can read that. But anyway, if I go ahead and stop it up here, the card memory use should drop back to 135. So our sphere there is actually using over 100 megabytes of video memory now for one sphere. And so that's fine if we're rendering one sphere. However, we only have 4 gigabytes. And so if instead of one, we've got like the simulation where all the balls come rolling down the ramp, and there's 700 balls, we don't have enough video memory. One way to fix that would be to make less output from the tessellation evaluation shader. And of course, the other way, and see, this is the great thing about the tessellation shaders, is if we just change the tessellation level a little bit, one parameter that we could easily change with the uniform, we can totally change the memory usage. So before we were using, whoa, 280? No way.
The same.
Didn't expect that one. Interesting.
Same.
280. Okay, well maybe there's some kind of block evaluation thing going on there.
Do 128 seconds.
This is often the 280. Okay.
Add more zeros.
Well, it might not test. Oh, I think it did. I think one other layer there. 280. Okay, never mind. It doesn't matter.
Maybe there's a minimum it takes
There could be.
to get to a certain point, and then
And we haven't managed to exceed it. At some point, it'll start ignoring us on this too.
Well, let's just tell it to draw more.
Okay, it
zeros.
looks the same as it did before, I think. I think we maxed it out.
Yeah.
Yeah, okay, never mind. That is not a reliable way to assess how much video memory we were using with our triangles that we drew. So now we know. Okay. So this one is, I think we're 4 on unified in the room. And actually my office computer has the special 760 that has 4 instead of the regular one that has 2. My cheap card buying advice, if you're buying a cheap card, see if you can get the version that has double the memory, because a lot of times like the 60 level, you'll be able to get the regular memory or twice the regular memory. And if you get twice, it will be able to do things that you wouldn't expect to be able to do with that cheap of card. It'll sort of hang with you as a usable item a little bit longer. Okay, unless you can get an upgrade to the next level and then do that instead. And then the other thing about the card buying is whatever money like you're going to spend on the card, just you pretend it's gone when you sell it, when you do it. You know, don't worry about converting it to assets. Like a lot of times when you buy something, if you're like, okay, well I used to have $200,000 and now I have a piece of real estate with a business on it. You know, you're like, well, I made a good investment, right? The cards are not like that. Don't think of it as an asset. Okay. And I have one more thing to talk about down there. Oh yeah, so the geometry shader, I just took out the geometry shader, but you can easily have the geometry shader back, and you can put the sphere inside a bigger sphere, which could be lots of fun. So for lab today, I will adjust it so that it looks a lot different. I can talk about it when lab comes. Basically, just adjust the tessellation evaluation shader and tessellation control shader a little bit, and make it look like this kind of weird figure with 6 or 8, yeah, this 8 points coming out of it. Let's show you then. Any questions?
When are we gonna bring view chairs?
Either Wednesday or next week. They're coming up. That's what you're looking for? Yeah. The basic difference with them is since they're outside the pipeline, you don't have like a specific time it's invoked. If you want to invoke it once per frame, you can. You just every frame you say, okay, let's go run the compute shader now and update everything's position. That's fine. You know, you're like, okay, let's do the compute shader, then let's do the normal pipeline. No big deal.
Insert it after the tessellation shader?
Once you call GL draw arrays, it's all kind of a block. So I don't think you get to put it in the pipeline.
So if you wanted to do a process for each of these fragments, then or did you just put it?
Well, if you want to process for each fragment, you got to do it in the fragment shader.
Oh, I mean, sorry, process for each primitive,
Each primitive.
like put out the tessellation shader.
Okay, yeah, I mean the answer there is probably geometry shader.
Yeah.
Or maybe tessellation evaluation shader, depending on what you do. But the tessellation evaluation shader does run once per vertex, and it doesn't give you access to the vertices. Or it could be tessellation control shader, which allows you to run on each patch, but you don't get one invocation per patch, and so it's hard to collaborate.
Yeah.
The geometry shader in a lot of ways is the most flexible shader stage, which is probably why it's the slowest.
Well, that sounds good.
Well, yeah, but the more general purpose and flexible and open-ended it is, the more difficult it is for the driver to manage it.
Yeah. It'd just be nice if we could put the compute shader in anywhere we wanted in the pipeline.
Yeah, it doesn't insert into pipeline, it's outside the pipeline.
That is an issue now, isn't it?
Yeah. Yeah, if they had a floating stage that you could insert anywhere in the pipeline, that would be even more of a pickle for the GPU manufacturer to get together.
I suppose.
Yeah.
Still, I can tough it up.
Right. Well, maybe the ray tracing shader will do as you want if they have such a thing.
No.
It's got to have some extensions. I was curious if there's probably no way to find out yet. Unless you're like a game developer or something. Nah. Eventually. Okay. Well, I'll let everybody go like 4 minutes early instead of making up more random irrelevant stuff.
Okay.
All right, close my terminal. I went down to 52 megabytes.